Hi, good morning, good afternoon, or good night. In this video, we will learn how to derive halftime equations. But first, let's remember the definition of halftime. Halftime, or T1/2, it's the time required for the concentration of a reactant to decrease to half of its initial concentration. Having said that, we can start deriving our halftime equations. So right here we have this table that will help us remembering our concentration time equations for our different orders. We also have the half-life equations, which are the ones that we're trying to figure out. So let's start with the zero order half-life. So right here we have the concentration time equation for a zero order reaction, and since we're looking for T1/2, the first thing we want to do is solve for T. So as you may recall, we have the current concentration, which is on our left side, and then we have K, which is our reaction constant, and then we have T, which is our time, and plus initial concentration. So let's go ahead and move the initial concentration towards the left side. So we would have current concentration minus initial concentration would equal to negative K times T. Okay, we're almost done. Well, solving for T. Then we have T. Okay, so K is multiplying T, so we would our K will be dividing these things right here. So we would have current concentration minus initial concentration over negative K. So don't forget the signs, okay guys? So, okay, now we already solved for T, but we're looking for T1/2. Okay, so by definition of half-life, it's when T equals 1/2 and the current concentration, it's equal to initial concentration over 2. So let's go ahead and start modifying this equation we just got. So we would have T1/2 equals initial concentration over 2. So is these, it's going to be this. Then minus initial concentration over negative K. So as you can see, we already have the formula for T1/2, but it's a little bit messy. So let's try to rearrange this equation. Okay, so before we move on, I would like you to show you a cool trick. So I don't know if you know this, but I call it the tortilla rule. So it's whenever you have one fraction over another fraction, when you're dividing one fraction by another. So you want to multiply the ones outside, and these ones will be your numerator. So A times Z will be your numerator, and B times Z will be your denominator. Okay, so this is a cool trick for you guys to use. So let's say we have, so just a quick example. So 4 over 2 divided by 1/2. So we already know the answer for this one, right? Let's see. I'm using like easy numbers so you can know it actually works. So we know 4 over 2 is 2, divided one by 1/2, it's going to give you 4, right? So let's see if this tortilla rule works. So you will multiply the ones that are on the outside. So 4 times 2 over 2 times 1. Okay, so we can eliminate the 2, cross it out, and we got 4. So yeah, it actually works. Okay, so that was a cool trick. So let's move on to our equation. So right here, we want to put rearrange this numerator because it's a little bit weird and messy. So let's try to simplify it. So we would have t1/2 so actually we have like a 1 right here. It's there, but we don't like write it. So we would have negative, yeah, okay, so be aware of the signs, over 2. And this fraction over negative k. Okay, so here we can actually apply the tortilla rule. So as I said earlier, all things, well, usually all numbers have a 1 on the bottom, so denominator. So we can just go ahead and put a 1 right here. So we're gonna apply the tortilla rule. So we have the ones, we're multiplying the ones outside. And this. So let's go. So t1/2, let me get another color. So t1/2 would be negative initial concentration, because the ones that are on the outside are going to be our numerator, over 2 times negative k, so 2k. And then we have negative signs, so we can go ahead and cross them out, cancel them out. So then our resulting t1/2 for the zero order reaction, it's going to be initial concentration over 2k. And let's see if this is true. If it's true, let's go to the table. Yeah, there we go. Now you know how we got the half-life equation. So this is a half-life equation for the zero order reaction. So as you can see, the t1/2 formula for a zero order reaction suggests that the half-life depends on the amount of initial concentration and rate constant. Yeah, so here we have the initial concentration and the rate constant. And a fun fact, it's that many of the known zero order reactions take place on a metal surface. Yay! Okay, so let's go ahead and see our table once more. So now we're going to work on the first order reaction. So this is our concentration time equation. And okay, so this numerator, it's going to be the same as ln of 2. You can do it in your calculator and you'll get this number. Here we have our concentration time equation for the first order reaction. As we can see, we have 2 different formulas, but actually they are the same. So a formula can be written in different ways just because we have different properties, especially with natural logarithms. So this one is given on your workbook and this one was given on the table. So let's see how the formula that was given in our workbook can look kind of this one. So, let's see what we have. So we have ln natural logarithm of the current concentration. And then we want to solve for t, right? So the first thing you want to do is bring the ln of initial concentration towards your left side. So you would have ln of current concentration minus ln of initial concentration, and that would equal to negative k times t. And from there, well, this is a personal preference, I guess. So if I can, I like to cancel out the negative signs because I don't like working with those. So I would just go ahead and multiply everything by the negative sign. So I will get positive kt, k times t, equals, so this one will be positive. So ln of initial concentration minus, okay, so this one was positive, so now it's going to be negative. So we would have ln of current concentration. Okay. And as you can see here, we can apply a property from natural logarithms. I don't know if you remember this from your pre-cal class, that whenever you have ln of a minus a ln of b, you can just put it in this form. So actually we're going to do that so it can like kind of simplify things. So kt would equal to ln, so our a in this case, it's going to be our initial concentration. So let's go ahead and put it in that format. Initial concentration over our b, which is current concentration. There we go. So we're solving for t. So t would equal to ln of initial concentration over current concentration and this over k. So let's see, is it similar to this equation? Yeah, so it's really similar. So as I told you before, there are a lot of ways of having the same formula, but it can look a little bit different, but it will still be the same. So right here, they have current concentration on the top and initial concentration on the bottom, and they have a negative sign. So we actually got like kind of the inverse. So we have everything positive, and we have initial concentration on top and current concentration on the bottom. Yeah. So we're on the right track. So now that we solve for t, we want to solve for half-life equation. So yeah, remember that t, it's going to be t1/2, and our current concentration, it's going to be initial concentration over 2. So let's go ahead and change our formula. Modified, well, it's basically kind of the same, but we have life. So we would have ln so we have initial concentration then over. So remember, like, all of the numbers like could have a 1 as a denominator, so it wouldn't change. Like 9 over 1, it's 1. So let's go ahead and put a 1 as a denominator for our initial concentration, because we will do the quote trick again. So I'll make this parenthesis longer. Okay, I'm gonna erase it because it's screwed. So let's do it a little bit bigger. Okay, cool. Okay, and then it was over the current concentration, but now that we're solving for half-life, our current concentration, it's going to be our initial concentration divided by 2. So let's go ahead and plug that. And this all over K. Yeah. So let's go ahead and do the quote trick again. So I'll choose another color. So we would multiply the ones that are on the outside, and those will be our numerator, and the ones inside are going to be our denominator. So ln of 2 times initial concentration over initial concentration. So as we can see, we can cancel. Okay, so let me over K, right? So as we can see, we can cancel out the initial concentration because we have it on the numerator as well as in the denominator, and this is true because they are multiplying, so we can go ahead and do that. So our final half-life equation for this first order reaction, it's going to be ln of 2 divided by K, and this will be our half-life equation. Okay, so as we can see, the half-life of a first order reaction is independent of the initial concentration of the reactant. So as we can see, there is no initial concentration on the half-life. Here. So measuring half-lives at different initial concentration is one way to distinguish between a first order and a second order reaction, which we'll be seeing later. So let's go ahead and see the table to see if we got the same answer. Well, the same formula. So yeah, we got it. So we have, okay, so if you plug in this number, well, if you plug in this information in your calculator, you'll get the same value, and it's going to be over K, which is what we got. Oh, okay. So now let's move on to our concentration time equation for a second order reaction. So this is what we have. So again, we're solving for T first, and then we're solving for half-life. Okay. So let's see what we got. So we have 1 over current concentration T, and then we'll just move this one to this side, minus 1 over initial concentration would equal to K times T. Yes, everything good so far? Okay, so let's go ahead and solve for T. T would equal to 1 over current concentration minus 1 over initial concentration, and these will be all over K. So right now we have solved for T. But we want to simplify our numerator because we want to make our life easier. So let's go ahead and do that. Well, we can actually leave it like this, and then we would go ahead and try to solve for t1/2 for half-life. So as we know, this is true for every order of reaction because it's the same definition of half-life. So whenever we have T, it's going to be T1/2, or in our current concentration, it's going to be our initial concentration over 2. So let's go ahead and change these little things. So let's rewrite our equation. Let me get another color. Okay, so we would have T1/2 equals to 1 over 1, yeah. Because 1 over 1 is going to be 1, so we have a numerator of 1. And our numerator, it's going to be initial concentration over 2. So remember our cold trick we learned before? Minus our 1 over initial concentration. And this is going to be all over K. So let's go ahead and try to simplify our numerator. So remember, the ones that are located on the outside are going to be our numerator, and the ones on the inside are going to be our denominator. Sorry. Okay, so let's go ahead and rewrite our formula. So we would have, 1 times 2, 2 over initial concentration minus 1 over initial concentration over K. Everything good so far? So let's go ahead and try to simplify it once more, our numerator. So let's go ahead and write T1/2 is, it's going to be 1. Okay, yeah, so we have the same denominator right here in our numerator. Okay, so that might sound a little bit confusing. So yeah, so right here, we're focusing in our numerator. So our numerator has the same denominator, which is initial concentration. So we just need to do a simple subtraction. So it's going to be 2 minus 1, it's going to be 1. So 2 minus 1 is going to be 1. So 1 over initial concentration divided by K. And K has a denominator of 1. So let's go ahead and apply again these cool trick we learned before. So it's going to be 1 over K times initial concentration. So let's go and see. Okay, so this will be our formula. So let's go ahead and see the table if we got the same formula. So yeah, we got the same. Okay, so note that a half-life of a second order reaction is inversely proportional to the initial concentration. So yeah, so I don't know if you remember, but inversely proportional means that it's going to be 1 over the value you're saying it's inversely proportional, which is true because you have initial concentration as your denominator. And this result makes sense because the half-life should be shorter in early stage of the reaction when more reactant molecules are present to collide with each other. Hopefully this video has helped you to understand better on how to get our half-life equations based on our concentration time equations of the different order of reactions. So thank you for watching this video.